Okay, in today's lecture, we will start to talk about new section. Right? So far, um, you learn about the mechanical properties of material. In there, you learn stress strain behavior of materials. Then that ductility and the elongation and all those kind of other properties you learn, right? So you now I hope you know how to get the information from a tensile test curve, right? So we will move to a new part, right? This is about imperfections in atomic and ionic arrangement, right? Which means because we have pure materials. That means one material may contain only one element, right? Other than that, but in nature, lot of materials are a combination of one or two or more elements, right? So uh, we can significantly change the properties of pure material by adding certain guest elements. Right? For example, if you think about brass and copper, when you add zinc to copper, you can have brass and it has different properties from copper. Right? So likewise, you can introduce guest elements or you can introduce certain defects, right? Those kind of things to a pure element to change their original properties or to enhance certain type of properties. So before learning about imperfections, we first need to identify the structure of uh, atoms in a particular element. Right? So how the atoms in a pure material can arrange. Sometimes in certain materials, the atoms can uh, be stable without joining with others. Some material make bonds to become stabilized and they have certain different properties from their parent materials. Right? So this atomic arrangement in materials we mainly can group into two types. One we call crystalline material, another one we call amorphous material. The crystalline material means the atoms are situated in a repeating or periodic array over a large atomic distances. That is, we call long range order exists in crystalline materials. That means the atoms are arranged in a periodic way and a repeating way. There's a pattern, and that pattern exists for a large atomic distances. We are talking about this atomic level distance. So we call that crystalline material, they have long range order. Right? For example, right, like this. They are arranged in an orderly manner. Right? The amorphous material means any material that exhibit only a short range order of atoms or ion. Right? That means that arrangement of that atoms are in order, but it is in a very short range. So such type of materials we call amorphous material. Right? Then you will hear in some fields about the crystalline structure in the future. That means the crystalline structure means the manner in which atoms ions or molecules are spatially arranged. How in the space that a certain atom or an ion or a molecule have arranged. That one we call the crystalline structure. Right? So in a crystalline material, right, the atoms, here these solid spheres we use to represent an atom. You know, atom contain electrons, nucleus, and those things, and a material is a um, it consists of lot of atoms. So how they have arranged is the one we call crystalline structure. Right? So when we try to visualize or when we try to explain the crystalline structure of a material, we consider atoms or ions as solid spheres with well-defined diameter. That means if it is a sphere, it has a diameter and it is a constant diameter. Right? Also referred as lattice means a three-dimensional array of points coinciding with atom positions. Or we can say it is a lattice structure. In that case, we consider the center point of each atom, that means each sphere, and when we connect that in three dimension, we call it the lattice structure. Right? So in crystalline material, you see the atoms are arranged in an orderly way. Right? So this is what we call crystalline structure or the lattice structure. So in crystalline structure, it is not convenient for us to consider all the atom to describe its properties. So we choose a unit cell. A unit cell means it's a small repeat entities in the crystalline structure. That means, for example, this is the unit cell of this structure. That means if you connect this type of several unit cells, you can make this whole structure. So the small repeat entity we call the unit cell in a crystalline structure. Right? So here is the definition. Right? You can read. The unit cell is the basic structural unit or building block of the crystalline structure. That's the definition. Right? So if we talk about a metallic in metals, their crystal structure, there are mainly we can categorize most of the metals into three types of simple crystalline structures. That means we can identify the patterns of the arrangement of the atoms. So we can identify basically these three type of pattern. One we call face centered cubic structure. Right? First one, face centered cubic structure. We call it is FCC. Right? FCC means the first letters of this name. Right? The second one we call body-centered cubic structure. Body-centered cubic structure, that one we give as BCC structure. BCC structure. Right? Another type we can name as hexagonal close packed structure. We call HCP. Other than these simple crystalline structures, there are more types, but we will basically learn about these three types in this lecture. So, when we characterize the crystal structure based on these types, we need to identify special features, right? So special features of a crystalline structure or the characteristic we can identify as unit cell edge length. One characteristic of a crystal structure is its unit cell edge length. We will talk in detail later. The second one we call number of atoms per unit cell. Number of atoms per unit cell. Third one we call coordination number. The coordination number. That means with how many atoms one atom is coordinated to. Number of nearest neighbor or touching atoms. That means when it coordinates, one atom can touch another atom, or it may act as a nearest neighbor. Right? So other characteristic we call APF, that is atomic packing factor. Right? So actually this part is a bit of difficult because you have to visualize the unit cell in 3 dimensions. You have to visualize, if you think about the unit cell, so how other unit cell will join to that one, and you have to visualize that one in 3 dimensions. We'll see whether you can understand this clearly. Okay. So we will first talk about FCC metallic crystal structure, right? That is, FCC means face centered cubic structure, right? So in this cubic structure, in its unit cell, atoms located at each of the corners and the corners of all the cube face. That means, okay, we are talking about a unit cell, right? In FCC structure, I will explain how the atoms are located. In FCC structure, there are atoms in each corner. If it is a unit cell, that means it is 3 dimension like this. In FCC unit cell, at the each corners there are atoms, and also there are atoms in the face of the cube, because this is a cube, right? We are talking about the cubic structures, right? Cube means it has this type of equal lengths of the sides, right? So in there, at each corner there are atoms, and at the face of the cube, that means this is the face of the cube, this is the face of the cube, this is the face of the cube. So this side, the other side, and the bottom, there are the faces. So in that faces also there are atoms, right? So this FCC structure mainly exists in metals such as copper, aluminium, silver, and gold type of metals, right? So this is the expanded view of this unit cell for you to understand clearly, right? Here you see at corners of the cube there are atoms, and this is in this face, right? This is the face of a cube, one face. Cube has how many faces? Cube has 6 faces, right? This is one face, this is another face, this is another face, right? Here another face, bottom another face, and here another face. So at each face there is an atom. That is the characteristic of face centered cube or the FCC cubic structure. So FCC crystal structure, you see that there are atoms in corners, but they are shared. This atom is not totally belongs to this unit cell. It is shared. We say it is shared with this corner atom with 8 unit cells. How? How? Because only a portion of the atom is belong to this unit cell, right? So how many unit cells you have to keep to complete this atom? Can you think? How many unit cells you have to combine in a one corner to complete this atom? Can you think about it? Maybe about 1 or 2 minutes. Okay, let's see. Think about this cone atom. To complete this cone atom, you have to put one unit cell in this side. That means in this direction, you have to put one unit cell, right? In this direction, you have to put another unit cell, right? Then in this side, you have another half part, right? Here you have another half now. So for that one, you have to have another unit cell in this side. So if you combine 4 unit cells for in this side, right, then you will complete half of the atom. So likewise, on top, you have to put 4 more unit cells to complete the other half. That means altogether to complete this cone atom, you have to join 8 unit cells, which means this each cone atom is shared among 8 unit cells. I hope you can visualize that. But this phase atoms, it is in the face of the cube. So this atom in the face, it is shared between 2 unit cells only. Half belongs to this unit cell, other half belongs to another unit cell. So that atom is shared with 2 unit cells only. But the cone atoms, they are shared with 8 unit cells. Okay. Now it's like this, right? Here it's clear to see, right? So this is your considered unit cell. So you have an atom in the face, right? You have to combine 2 unit cell to complete this face atom. That means this face atom shared with 2 unit cells. Look at this, right? So how many unit cells in there? 1, 2, 3, 4, 5, 6. Other side 7, 8. That means that cone atom we can complete if we combine 8 unit cells. That means cone atoms are shared with 8 unit cells. Okay. I think you can see clearly from these two figures how the atoms are shared in a unit cell. Right? We are talking about FCC metallic crystal structure. Then we'll identify that before mentioned characteristics. Right? H length means it is the length of the cube. If the crystalline structure is FCC, the length of one side we call the unit cell edge length, right? So usually the radius of an atom we can consider as a constant value. So is there any way if the unit cell edge length we denote it as simple A, right? That means if this is edge length, if it is simple A, can you relate this length with this uh, atomic radius? Atomic radius means this is the atom, so this is the radius. So can you get a relationship between this edge length and the atomic radius r? Can you think about it? So though they are here, we have drawn it for the visualization purpose. They are actually located like this. They are touching, right? In that case, this is A, right? This is R. This is half of the R. This is the radius. R. Sorry, this is atomic radius R. So this is 2R. This is R, and this is R. You can use the Pythagoras theorem to get a relationship between A and atomic radius R. Right? So other than that, I told you number of atoms in the unit cell is specific to the type of structure. I will say the number of atom in the FCC unit cell is 4. How? Because at corners, this atom is shared with 8 electron, 8 unit cells. So you have 8 corners in a cube, and if you think it is 8 atoms in corners, but that 8 atoms are shared with 8 unit cells, right? So to find the portion of the atom come to this one unit cell, how we calculate? We have to multiply that 8 by 1 over 8, because there are 8 unit cells in the corner, but only 1/8 of the atom belongs to 1 unit cell. So that is 1. Plus you have atoms in the face, but it is shared with only 2 unit cells. So you have 6 faces, but in 6 atoms are shared with this one shared with 2 unit cells, right? In that case, you have to divide that 6 by 2 to get the number of atoms that belongs to the cube, this unit cell. That is 3, right? So the number of atom in the FCC unit cell here is 4. 4 plus 1. That means 1/8 of the 8 cone atoms, right? Half of the 6 face atoms. That is total 4. Right? Then the coordination number of FCC cube, we call it is 12. We can find it as 12. How? If you think about this center atom, right? It has this 4 touching atoms, right? So other than that, these are nearest neighbor atoms. So that is 4 in 4 phases. 1, 2, 3, 4. Right? So from the other side, unit cell, from the unit cell located in this side, there are 4 another nearest neighbor atoms. So altogether, there is 12 coordination number we'll have in this FCC cube. Right? You have to think about this in 3 dimensions. Okay. So the atomic packing factor of a crystalline structure we define as volume of the atoms in a unit cell divided by total unit cell volume. Right? So you know now number of atom in FCC unit cell, that is 4. Then you have to get the volume of the atom in a unit cell. Right? So total unit cell volume you can find if you know this edge length. Edge length means this length. If you know this length, you can find the unit cell volume. So you can calculate the atomic packing factor for the FCC cube as 0.74. So this atomic packing factor value, then the coordination number and the number of atoms in a unit cell, all these are specific to this FCC cube, the characteristics of FCC cube. So you can think about how to get this value, right? In the next lecture, I will be conducting it as an online Zoom lecture. So if you need, I will explain you how to get this value with the calculation. Okay. So this is FCC cubic structure. I will explain other two in separate recordings. Okay, in the previous recording, I explained you about the face-centered cubic structure and its features. For example, the number of atoms in the unit cell and how to find that one, coordination number, and atomic packing factor. Right. So I left you certain things to calculate by yourself, but I will explain that now. So I told you that this unit cell edge length, that means the side of this length. So this can be, we can put as A, right? This length is A, right? So the radius, atomic radius is R. So you can have a length of a unit cell if you know the atomic radius. So for that, you can have a relationship with A and the R. So sorry, what you can do is, I told you this is the diagonal of this face, right? These atoms are touching each other. So in that case, this is this length 2R because the radius is R. This is R, the radius, and this is R. Right? This is A. So you can apply the Pythagoras theorem and it will come as, I will write like this. You check whether it is correct or not. Okay. Is equal to so this is the diagonal length, right? So that length, how much it is, we can write 2R, so 2R plus R plus R to the power 2. Yeah, applying the Pythagoras theorem. So this length is equal to square root of this one and square root of this one. This both sides are A because this is a cube. Right? So this is A square plus A square. Okay. So you can simplify this equation like this. You can write. So you can get the relationship by simplifying this one. It will become as A equal to A equal uh, to you will get is you will get the relationship between the atomic radius and the unit cell edge length as A equal to square root 2 R. Right? This is the relationship. Now you have a relationship between A and the atomic radius. So when you are going to calculate this atomic packing factor, you can get this answer. Right? You can do it like this. Right? So this is the volume of atoms in a unit cell. In FCC unit cell, there are 8 atoms in a cell, and to get the volume, you have to multiply your volume of a one atom by 8. So volume of a one atom, how we can write, is equal 8 into 8 into 4 over 3 4 over 3 R cube. This is the volume of a sphere. Right? This is the volume of a sphere. There should be 5 terms here. Right? This is the volume of one sphere. That means one atom. Atom radius is R. So there are 8 atoms in a unit cell. Right? Then total unit cell volume. Right? To get a numerical value, you can substitute the unit cell volume in terms of atomic radius. That means here A equal to square root 2R. So you can put here. Right? So this one 2 root 2 R to the power 3 because it's the volume of a cube, right? So one side is 2 root 2R, that is A, that means this length A, and we have to get the cube, right? So once you multiply this one, you will get the value as 0.74. This is how we calculate that, right? So I hope now this is clear for you. Now let's move to the next type. Body-centered cube metallic crystal structure, we call PCC structure. Right? So, so in here, the way the atoms located are different from the FCC cube. Right? Here, there are 8 atoms in the corner, and similar way, one atom is shared with 8 unit cells, right? Because these are corner atoms, and there are 1 atom in the center. right? So in a BCC crystal structure, atoms located at all 8 corners and a single atom at the cube center. So this is the structure of BCC metallic structure, right? So can you tell me how many atoms are there in this type of unit cell? It is 2 because there are 8 atoms in 8 corners, but they are shared with 8 unit cells. So 8 into 1 over 8, that is 1, and there is one single atom in the center of the cube. So total number of atoms belongs to BCC cube is 2, right? So similar way, you can get a relationship between edge length and the atomic radius, but not the way you did for the FCC structure, right? Because the atomic arrangements are changed, different, right? So here, how we get a relationship? So you see in here, they touch, but not like previous time. So these will touch in this diagonal length. Right? If I draw it, right? If I draw it from this point to this point, it touches each other. Right? So which means from here to here. So in that case, you have to consider this triangle when you get the relationship. So this is, you can calculate, right? 2r plus r, that is 4r square, right? Actually, this is 4r square means to the whole it is square, right? Not because this is 2r, then that is 4r. When you apply the Pythagoras, that is uh, 4r, the whole term, we have to get the square, right? Or else, if you take the atomic diameter is 2r, that is now 4r. That is also possible. I think this equation I have written by considering atomic diameter is r, right? So I will change this one. Right? I will change. Right? So I will consider this. Sorry. I will consider this triangle, right? So if I consider atomic radius is r, now here this is 4r, because in this direction it is 4r, and square is equal to this is this length. How you get it? This is a, this is a, so this is the diagonal length. So that one a square plus a square 2a square, then this length is root 2a, then if you get the square, that is 2a square, 2a square plus this is a, right? That is a square, right? So you will get here the answer as once you simplify this side, there is 3a square, this side 4r square. So when you get the root for both sides, so you will get the a equal 4r over root 3. That is the relationship between edge length and the atomic radius for a BCC structure. right? The coordination number is 8 because it's simple. If you consider the middle atom, there are 8 corners and 8 atoms in there, right? So atomic packing factor you can calculate as I did previously. So you will get it as 0.68. This is the atomic packing factor for BCC structure. Okay. So this is the third time I explained you earlier. This one we call the hexagonal closed pack structure, HCP structure. You see the atomic arrangement. Please observe the atomic arrangement. Here, this is the hexagonal, right? So this height is C, and this is, in this case, this is we define as A, length of one side. So usually C over A ratio will be around 1.633, right? The way if I explain the atoms are arranged, so there are 3 complete atoms in the middle, right? All 3 atoms belong to this unit cell, and there are corner atoms. There are 6 corner atoms, right? So one corner atoms shared with how many unit cells? This side, this is 1 unit cell. This side 1, this side 1. So in one plane it is 3. From top there are 3. That means one corner atom is shared with 6 unit cells in here. Right? So in that case, if you calculate the number of atoms in the unit cell, the center atom, the face atom, this one is shared by 2 unit cells. Okay, then when you calculate the atoms in the unit cell, here is 3, right? Here half, then altogether 4, right? Then there are 6 atoms in the corners, but they are shared with 6 unit cells. So 6 into 1 over 6, 1. From this side there are 1. So altogether there will be 6 atoms in the HCP unit cell, right? When you find the coordination number, right? Here if you consider this atom, there are 6 atoms here, 3 atoms here, 3 atoms on top. So altogether there will be 12 coordinated atoms, right? So similarly, you can calculate the atomic packing factor considering this ratio as well, right? So these are common metallic structures. I explain you the FCC, BCC, and HCP crystalline structure. So let's do one example. Can you please read the this example? Determine the density of BCC ion. That means iron has BCC crystal structure which has a lattice parameter of 0.2866 nanometer. Atomic mass of iron is 55.845 grams per mole. So how you find the density of BCC ion based on these information. Let me ask first, what is a density? Density means the mass of a unit volume, right? So in this case, here lattice parameter means the A value, that means the edge length, right? So if you consider a small unit cell of BCC ion, if you know the unit cell volume and the mass of the unit cell, then you can find the density, right? If I type these things, density, I will give the symbol rho equal weight over volume, right? It means the weight over volume, right? Forget about this one first. I will start from the first principles, right? That means the basic, right? Then if you consider a unit cell, one unit cell, you can try to find the unit cell volume and the unit cell weight. Then what is the volume of the BCC unit cell? How you find? You have the lattice parameter, that means edge length. Then if you multiply one side from other side and the height, you can get the volume, right? So you can write it like this. Design nanometers, no? So we can convert into maybe meters, right? To convert into meters, you have to multiply by 10 to the power minus 9 to convert it into meter. Okay, then this is the one side, the length, right? So you have to get the cube to get the volume of a BCC cube, right? So this will come as meter cube in unit of meter cube now, right? Okay, now mass of the BCC unit cell for iron. How you find? So atomic mass is 55.845 grams per mole. That means how many atoms? Per a mole, there are Avogadro number of atoms, right? Per a mole, there are Avogadro number of atoms. So to find the weight or mass of one atom, you have to divide this amount by Avogadro number, right? So we'll start. what you can do is you divide this 55.845 by the Avogadro number into this is the uh, weight of one atom, right? Then how many atoms are there in a BCC unit cell? In a BCC unit cell, there are 2 atoms in it. So this is the weight of one atom, but iron BCC unit cell, it has 2 atoms. So this within bracket means I multiply this by 2, right? Into 2. It's like this, right? So this is the mass of the unit cell. This is the volume of the unit cell. What you should do now, find the density. You divide this one by the volume. Then you can get the density of BCC ion. Right? I hope you can get the answer by doing the calculation. Right? Now here the unit is grams because we will convert this 555.845 into kilograms or anything. So unit will be here, it's gram. Right? So this is how we use the information about the unit cell to calculate certain parameters. Morning everyone. Welcome to today's lecture. So last week we started a new section. Sorry, before that I need to, I hope that you reached my message about the assignment, right? The assignment 1 I have uploaded to LMS, and probably from my part there will be 2 assignments, right? So from after next week I think Professor Dr. Rajitha will take over the course to continue with the other parts. So for the assignment 1, I basically wanted to check your knowledge on that mechanical properties of materials, right? So in there I have provided you the necessary um, instructions. So what you have to do is either if you have a laptop, so you can type that answers to that in that laptop, and you can save it as a PDF or in a Word format, and you can name your file with your index number, and then you can submit it to the LMS, right? You should submit it through LMS only. Please don't send it to my email or my WhatsApp. Right? I won't accept because you know there are more than 160 students in this course. So if I receive all your assignments to my email, then I won't be able to clearly collect those, and there are high chances to miss the your submissions. So if you submit your assignment to LMS, you will receive a message after you submit it. So you can have evidence about your submission. So please make sure you submit your assignment before the due date, right? It is, as I remember, it's 29. So I think that's 2 weeks time. So please submit it within that day. If you have any type of difficulty to submit the assignment because of the uh, uh, because you don't have a laptop, right, or you don't have internet facility, you have to inform me first, right? But that the day you inform should not be the last date of your uh, submission deadline, because some people, they, if the deadline is today, they today email me that I don't have internet, I have a flood here, so I cannot submit like that. So that kind of excuses are not acceptable. You know, if you don't have a laptop, you know that, right? Because you cannot wait until the last day to complete the assignment. You have to try it for at much more earlier. So in that case, if you, at least if you inform me before 1 week to the due date, then I will accept it as a reasonable one reason. Otherwise, I won't accept the reasons, excuses you me at the due date. Right? ඒ කියන්නේ දැන් සබ්මිෂන් කරන්න තියෙන අන්තිම දවස් අද නම් මට අද මේ ප්‍රශ්නයක් තියෙනවා, අද මට සබ්මිට් කරන්න බැහැ කියලා එවන ඊමේල් වලට මම එක්ස්කියුස් එකක් දෙන්නේ නැහැ. ඔයාලට මොකක් හරි ප්‍රශ්නයක් තියෙනවා නම් ඒක මට කලින් දැනුම් දෙන්න ඕන, සතියකට හෝ පුළුවන් තරම් ඉක්මනට. එතකොට මට ඒක කන්සිඩර් කරන්න පුළුවන්, ඔයාට ටයිම් එක්ස්ටෙන්ෂන් එකක් දෙන්න පුළුවන් ඔයාගේ සබ්මිෂන් එක කරන්න. අද එහෙම නැතුව ඩෙඩ්ලයින් එක කියන්නේ අද සබ්මිට් කරන්න තියෙන එකට අද දවසේම මට කියනවා නම් අද කරන්න බෑ කියලා, ඒක මම පිළිගන්නේ නැහැ. Right? Another reason is another thing I need to remind you is if you don't have a laptop to prepare the answer script, you can write it in a paper, the answers, and I think now most of you have phones, so you can take a photo and save it as a PDF and name the file with your index number, and you can upload that one also. It is also acceptable, right? So this is all about the way you submit the assignments. So the next assignment probably I will give you next week, right? So that one also I will give you 2 weeks time, so I think it is a reasonable time. So last week we started a new topic, the imperfections in atomic and ionic arrangements. Right? So actually, why we talk about these imperfections? Because we always assume the materials are, if you say it's aluminium, we assume it's a pure aluminium, right? But in practically, that purity is not 100%. Right? So that's why people, actually that is kind of an advantage. Sometimes these impurities present in pure materials, they worsen their properties in some cases, but sometimes they are acting in a favorable way. That means if we talk about the strength of material, presence of some kind of impurities will reduce their strength. But if you add certain different element, so that means certain different purity, that impurity atoms, so you can enhance the strength or the other properties like corrosion resistance, those kind of things. So in that case, the imperfections are important when you choose certain material for a specific application. So I told you, I teach you already about that crystal structure, right? Then common crystal structures that we can find in metals, right? So in all these cases, we assume they are pure metals, right? We assume they are pure metals, and we identified certain characteristics important characteristics of the crystal structure. Okay. Then we will move. We know that in practically they are not that perfect. There are defects. Okay. So let's learn the possible defects that can happen in crystalline materials. Okay. One type of defect we call point defect. Right? That means they are localized disruptions in otherwise perfect atomic arrangement in a structure. Certain points there are defects, so we call point defects. Right? In general, you can identify basically 4 types of defect in a perfect crystal structure. One we call a vacancy defect. We'll go one by one. The second one we call interstitial defect or interstitial atom. The third one we call a small substitutional atom. Fourth one we call the large substitutional atom. Right? So what is a vacancy defect? So these yellow color circles represent the atoms. So here you can see there is a missing atom. So we call it a vacancy. Right? Here the definition, a vacancy is produced when an atom or an ion is missing from its normal site in the crystal structure. This is usually an occupied site, but that atom is missing. So there is a vacancy. Right? So vacancies are introduced into metals and alloys during solidification at high temperatures or as a consequence of radiation damage. Right? So this vacancy, usually in every material there are vacancies, vacancy defects, and those vacancies they are sensitive to temperature. Right? So we can express the number of vacancies in a certain material using this equation. Right? This equation NV equal N exponential minus QV over RT. Right? So we'll see what are these different symbols represent. Right? NV. Here NV is the number of vacancies per centimeter cube. Right? Number of vacancies at a certain temperature per centimeter cube. Then this N is the number of atoms per centimeter cube. Right? Then QV is the energy required to produce 1 mole of vacancies. Right? A QV means the energy requirement to produce 1 mole of vacancies. The units can be calories per mole or joules per mole. R is the gas constant, right? It comes with 2 units in joule term and in calories, right? So it is commonly we can say 8.314 joules per mole per Kelvin. Okay? T is the temperature in degrees in Kelvin. You know, to measure the temperature, we have different units. Kelvin is one type of unit we use to measure the temperature. How you convert Celsius to Kelvin? You have to add that, let's say the temperature is 20 degrees Celsius. To convert into Kelvin, you have to add 20 plus 273, the constant. So that new value, that is 293 value, is the temperature in Kelvin, like. Right? So these vacancies sometimes we can naturally they can exist, and we can intentionally add pure or perfect materials to alter their properties. We will do an example on this later, right? How to calculate the vacancies in a crystal material. So the interstitial defects, if you check the figure, I think it's very clear what is a interstitial defect. An interstitial defect is formed when an extra atom or ion is inserted into the crystal structure at a normally unoccupied position. Right? You see the center position is not a lattice point. This position is not a lattice point. Usually at this place there cannot be any atom in the crystal structure, but now there is an impurity atom in this location, in this unoccupied position. So we call this type of defects are interstitial defects. Then substitutional defects. We talk about two types. One is substitution of a small atom to a usually occupied position. Other one is substitution of large atom in a usually occupied position. Right? So in this case, one atom or ion is replaced by a different type of atom or ion. The substitution atom or ion occupy the normal lattice side. So this is the normal lattice side, but the atom in this normal lattice side is different from the other places. So it's a guest atom, right? Here also the same. It usually occupy the normal lattice side. The substitute atom or ion can be smaller or larger than the atoms or ion in the crystal structure. Depending on the size of the substitute atom, surrounding interatomic spacing will change. You see, now here a small atom substituted. Now you see the lattice lengths, they have changed. That means the crystal structure is disturbed. Right? In that case, here it's a large, so there is a kind of expansion. Right? The surrounding, that means interatomic spacing, change because of these substitutional defects. The substitutional defects disturb the surrounding crystal. Right? Then substitutional defects can be introduced either as an impurity or as a deliberate alloying addition, and once introduced, the number of defects is relatively independent of temperature. Right? In naturally, there can be this type of substitutional defects, or we can intentionally add, for example, to make alloys. Right? We can intentionally add impurity atoms to alter the properties. Right? So once it introduced to a occupied lattice position, it is usually this defects, number of defects, relatively independent of temperature. Right? Examples of substitution defects include incorporation of dopants such as phosphorus or boron into silicon. We will see later. So we can introduce silicon, phosphorus or boron into silicon to alter its silicon's properties. This is a kind of example. Right? So this is an example to calculate the concentration of vacancies in copper. Right? So this is calculate the concentration of vacancies in copper at room temperature. That means you are asked to consider room temperature as 25 degrees Celsius. What temperature will be needed to heat treat copper such that the concentration of vacancies produced will be 1000 times more than the equilibrium concentration of vacancies at room temperature. Assume that 20,000 calories are required to produce a mole of vacancies in copper. Right? The lattice parameter of FCC copper is 0.36151 nanometer. So, in order to solve this, we have an equation. This one we have. I will put it in here for your easiness, right? Here, in the first part, calculate the concentration of vacancies in copper at room temperature. That means room temperature is 25. So they are asked to calculate the NV value. Right? So to find NV, what are the other data you need? N. N is the number of atoms per centimeter cube. It is not given, but the required data to calculate N is provided. What is the data? FCC copper, it says the copper has FCC crystal structure and the lattice parameter, that means the edge length, is this amount. So what you can do is you can find the volume of the FCC copper unit cell. I am telling you the steps. First step, you can find the volume of a FCC copper unit cell. What is the volume? So this is length of one side of the cube. So you can get the volume of a cube. That means the unit cell volume. So in FCC copper, FCC means what? Face-centered cubic structure. So in a face-centered cubic structure, how many atoms are there in a unit cell? Can you recall? Can you recall? There are 4 atoms in a FCC crystal structure. So you know the volume of a copper unit cell. In that volume, how many atoms are there, you know. So in a unit cell volume, there are this amount of atoms. If so, what are the number of atoms in 1 centimeter cube? You can find. Right? That is the step to find the N value. So after that, the question is easy. QV. QV is the energy required to produce 1 mole of vacancies. Right? So QV is 20,000 calories. Calories per mole. So the R, the gas constant, you have to use 1.987. Then T is the temperature in Kelvin. It is at room temperature 25. So to convert to Kelvin, you have to add 25 plus 273. So once you put all the values, you can calculate the number of vacancies per centimeter cube at room temperature in copper. That is how you find the answer to the first part. So now you know at room temperature how many vacancies are there in copper. So what's the second question? What temperature will be needed to heat treat copper such that concentration of vacancies produced will be 1000 times more than the equilibrium concentration of vacancies at room temperature? So what you do? You have to do a reverse calculation. Now you know the NV value. NV means what? 1000 times the vacancies at room temperature. We already calculated the vacancies in room temperature. So we need that vacancy is to be 1000 times the concentration of vacancies at room temperature. So this is 1000 into vacancies at room temperature. This part. N is the same, QV value is the same, R is the same, so you have to calculate T. Right? You have to do the reverse calculation. So you try this at home, and next week we will see the answers. One thing I need to tell you is that some students send me their questions regarding the examples in lectures to my WhatsApp. I really cannot see the phone for that kind of lengthy questions and answers. So please send it to my email, then I can reply you easily. Right? Don't send it to my WhatsApp account. Right? So this is all about the defects in crystal structures. So that those defects first we call are point defects. That means at points the possible defects. Dislocations are not the point defects, they are line, we call line defects or one-dimensional defects. That means the line of atoms are misaligned. We call dislocate. Right? If we have a knee joint, right, it can dislocate. That means there are line imperfections we call. Right? So these dislocations we introduce usually to a crystal during solidification of the material or when the material is deformed permanently. Right? There are basically three types of screw dislocations, what we call screw, edge, and mix dislocation. So we'll see what is a screw dislocation. Right? Here is a part of material. There are atoms in here. Right? So let's say you cut through this plane, this piece of material. You cut through this plane. Right? You cut. Right? Now you consider this part. Right? Then you pick this cut section from this point and you dislocate it to downside. It's like this. Okay, so here this is a crystal. So if we draw the lattice structure, it will be, we can draw like this. You see this point is like the point here. Right? Initially it was in here. This point initially was in here. When the dislocation happened, what happened? The point here is not there, it is in here. We call it as a dislocation, and we call this type of imperfection as a screw dislocation. Right? So this part, it has explained how to do it. Right? You just have to simply see at the figure and see the difference. This is not a perfect crystal now. Right? So edge dislocation is, we have a perfect material. We cut in one plane and we insert a line plane of atoms. And we half insert it to the material like this. So it is like this point that we inserted. Now there is an imperfection to this material. So this type of imperfection we call edge dislocation. Okay. There can be material who has this You see, this is a screw dislocation. This point initially was here. Now it is here, right? So this is screw dislocation, right? Now here there are inserted atom plate. So this is a edge dislocation. So we call the mixed dislocation. Right? These are about the line imperfections of materials.